Okay, so today we're going to be looking at calculus in motion. We're going to do some examples of something that, the kind of problem that we can't do in general physics because we don't have the math for it. So first I have just a couple slides on the meaning of calculus symbols, which we've already gone over this quite a bit. The definition of velocity is, go ahead.
When is our first test?
I believe it's a week from today.
Is it a lab time?
Is
it during lab?
Yeah, during lab time.
We have the same exam for everyone else?
No, you'll have at least one different question from them. Otherwise, calculus, what? That's just superfluous. You might have an occasional homework problem. Okay, so velocity is defined as the limit of change in x over change in time as that change in time is approaching zero. And so calculus is just applying that limit. In the limit, as delta y approaches zero, delta y becomes dy. So dy just means we're in that limit, right? You know this, right? No shockers there. So that means we can write the velocity as derivative of position with respect to time. And of course, I'm saying velocity. There, now it's velocity, right? That's all it takes. And similarly, acceleration is the limit as time approaches zero of delta v over delta t, or in other words, the derivative of velocity with respect to time. So what we want to see today is how are we going to use this? Now, in the first lecture, I actually went through some examples, but let's do a couple practical ones. Now, this first one is just an equation. It's an equation that's somewhat reminiscent of a Maxwell-Boltzmann distribution. Check it out when I get a phone call. Okay. Since I never have the ringer on, it's the only way it buzzes in my pocket and it shines through. Just a little note of warning, though. It can't mean this summer I was sitting in the second row, and during the sermon, I got internet would work like once every 30 minutes or so. And so it connected, got a message, and it flashed. And this lady photographer came over and was just ripping into the people sitting behind me about taking a flash photograph during the program. And I tried to tell her, no, I'm pretty sure that was my phone when I got a call or a text, but she wasn't listening to me. And anyway, so when people are videotaping, make sure you don't have it so it'll flash randomly. Lesson learned. My parents were all, that's so unchristian of her. So here's an example. Say you have the velocity is given as a function of time. How can I find from this the instantaneous acceleration at any time? Answers. How can I find instantaneous acceleration? Yeah, just take the derivative. And I'm going to go to the next slide before I do any of the work. Right now, we're just thinking about it. So that would be to take the derivative. How would I find the greatest speed, the maximum speed? How do we find minima and maxima in calculus?
Would you take the limit as it approaches infinity, or?
Well, this approaches zero as you approach infinity.
Oh, right.
Minima and maxima. Okay, let's leave this to the next graph and then we'll discuss it. When is it at the greatest acceleration? Steepest slope. Okay, so steepest slope. Which means that we'll have to find the slope and then find the maximum of the slope. And then how far does it travel in 10 seconds?
Oh, and that's for the minimum and maxima, that the slope's equal to zero, right? So that's what acceleration
That is right. Okay, so Alex got that answer, and Gila said take the integral from 0 to 10 seconds. So we have our methods. Now let's look at the graph, because to me a graph says a lot. If you look at the graph, we said the instantaneous acceleration is just going to be the slope of the graph. So we can look at this slope, and we could at any point say, right here, change pen color, right here the slope is like, so the acceleration is negative with roughly that value. With calculus, we do this slope as the derivative. Then we had, how do we find the greatest speed? Who can identify the greatest speed on this graph? How do you identify the greatest speed? Yeah, you can see it. It's the highest it gets, right? So there's our greatest speed. Okay, so something like that. So we can identify when it occurs and what it is by looking at the graph. Our mathematical method that Alex gave us. Go ahead.
Never mind. Isn't it 0 when it's at the very high, maximum height?
The slope is 0. And that's where I was going with this. As Alex said, we set this, we take the derivative and set the derivative equals 0 because the derivative is the slope. And of course, anytime the slope is 0, you're going to be changing from going up to going down or going down to going up, unless, of course, it's an inflection point. You guys know inflection points, where it comes up, goes like that. You can have those that are neither minimum nor maximum, so you have to go through and do further analysis to see which one each one is. Then we had the greatest acceleration. So if you look at this graph, can you tell me where the greatest acceleration occurs? Roughly speaking.
0 to 2.
Okay, it's going to be somewhere around here for greatest acceleration. And just to mark these, somewhere, well, right there for greatest speed. And then finally, how far does it travel in 10 seconds? How do you find that? You take the integral from 0 to 10 seconds. But the integral means the area under the graph. So I'll give you an approximate value, and then we'll go ahead and calculate. So an approximate value, I'm just going to say, let's suppose that I make a straight line stick figure here. Now, is that a perfect fit? No. Ideally, I have about the same amount of undershoot as I have of overshoot. And it looks like what I drew is roughly fitting that. And so if I take the area under that triangle, that should be pretty close. It's not going to be exact, but it should be pretty close. So let's just do that real quick. I have a triangle, and the triangle has, this side here is 10. Of course, that's neither the base nor the height, but it has, well, actually it is. It's the base. And it has a height of, let's call that 10.9. So if height is equal to 10.9, and that was meters per second, and the base is equal to 10 meters, then what's the area? 1/2 base times height, which would be 1/2 of 10.9 meters per second times, oh, that's seconds, not meters, times 10 seconds. So half of 10.9, well, half of 10 is 5. 5 times 10.9 is going to be 54.5. And notice my units now, meters per second times seconds is meters. So it gives me that for the distance. Now let's do careful calculations instead of doing rough and random. So starting with the beginning, and I'll come back to this, find the instantaneous acceleration. So now we're going to apply calculus, and we're not going to go through and do everything super explicitly because you did that here. You should look at Gila's. It's perfect for what I can see so far in a quick glance. So I have dv dt. My v is written right here. So I'm going to take that derivative. What rule am I going to have to use to do this derivative? Not the chain rule, the product rule. Now, you could go through and use the chain rule depending on how you do it as well. But the product rule is what I'm looking at. So it's, 10t squared is my first function. E to the minus 0.7t is my second function. The first one times the derivative of the second is going to be derivative of an exponential. You bring down the derivative of the exponent. Derivative of minus 0.7t is just minus 0.7. And then the original exponential. I actually like to put zeros to make it clear. So that's the first term. And then the second term plus the derivative of the first, which is 20t, right? We can do that in our heads. We don't need to show it explicitly now. And then multiplied by the second one. So that's equal to 7t squared. Whoops, let's put it the other way. 20t minus 7t squared e to the minus 0.7t. So for any time, that's my acceleration. Right, we're able to find that. We call this analytically when we're able to do the math. At the end of today, we'll have a problem where we can't do the math, where it's non-analytic. Okay, when is the speed the greatest? Well, when the acceleration is 0. So let's set and I have to factor this once more to make things really clear. How many solutions do I have?
2.
Actually, 3. I separate out so you can see 3 different pieces. The first one, Tm. At what time, Tm, would this equation be 0 based on the first term?
T0.
Yeah. So Tm equals 0
That's why I said 2.
or, well, there's 2 we're not going to count. Okay, then the second term, 20 minus Tm equals 0. What's the solution there? Minus 7 Tm.
On the line above, after you close parentheses, what's the subscript? Is that F? Is it E?
Okay, this right here, that's 20 minus 7 Tm,
E, right?
and then e raised to the minus 0.7. It's not a subscript, that's e
Okay.
for exponential. So there's my second answer. Tm is 20 over 7, which would be just a shade under 3, right? Because if it was 21 over 7, it would have been 3. And then my third one, or e to the minus 0.7 Tm equals 0. What value for Tm would make that equal 0?
Well, what?
What value for Tm makes e to the minus 0.7 Tm 0?
We do natural log of those?
We could do the natural log of both sides, except for natural log of 0 is it's minus infinity, undefined. Tm, as Tm approaches infinity, because that's minus infinity, I'd have minus infinity equals minus 0.7 Tm if I did what you said. Cancel the minus signs, divide by 0.7, infinity divided by 0.7, still infinity. So Tm approaching infinity. So I had three answers. Tm is 0, Tm is 20 over 7, or Tm is equal to, is approaching infinity. Now, of course, this is the tricky part to make sure I did my math right. That's a little less than 3. Let's just make sure on the graph, was that a little less than 3? Yes, because 3 would have been right there. So it matches our graph. Yes?
Is it acceleration equal to 0 or velocity equal to 0?
To find the maximum velocity, you're setting the derivative of the velocity, which means acceleration, equal to 0. So we were saying acceleration is 0. Just remember the rule, though. It's important to remember to maximize any function, whether it's position or velocity or acceleration. You take the derivative of that function set at 0. So here, because it was velocity, the derivative of velocity was acceleration. So if you just say when the acceleration is 0, it's at maximum, it's only the velocity that's at maximum. Okay, so we were able to find the maximum. What are these other two? The two that I rule out here. Why is that one? Whoops, I didn't mean to do it in that color. Why is, yes, green. Why is this one not my answer? It's what?
Because it's obviously not the greatest.
Okay, because it's obviously not the greatest, because it's a minimum. That's when the speed is at a minimum. Why is this one here not the answer? It's, again, a minimum, right? Because this finds only the extrema. Whether, it's an extrema, that is, it's either maximum or a minimum. Put them together in the plural, it's extrema. Well, singular is extrema, plural is extrema. It's an extrema, and it's an extremum if the slope is 0. So we found all the extrema, but the only one that was a maximum was this one here. And of course, looking at the graph, you say, oh yes, this function can never go negative because it's times squared. Times squared can never be negative. And exponential, the exponential can never be negative. So the times when it's 0 have to be minimum. All right, the next one. We found the greatest acceleration. Nope. We found the greatest speed. How do we find the greatest acceleration then? Say that, Corso? No, I will not. Go ahead, Vila. Well, what was the rule I just gave you for finding the extremum?
You just set every function to 0 and take the derivative?
Other way around.
Oh.
Take the derivative and set that equal to 0. So when derivative of the acceleration with respect to time is equal to 0.
So that's when the jerk is equal to 0?
That's correct, when the jerk is 0. And so now we just take our function here, which was derivative of that function. It has 3 things. So I'm going to use the product rule in triplicate. Yay. So I'm going to have that's equal to derivative of the first is 1 plus derivative of the second times the other 2 plus the derivative of the third times the other 2 When that's equal to 0, then I'm going to have a maximum or minimum for the acceleration. And so this one here, it does have e to the minus 0.7 tm on everything. So I can factor that out. Doesn't have a tm with everything though.
Is the first one the derivative only the first one taken? What's the first term?
The first one, I took the derivative of the first term, which was Tm. I was doing this form of the function here.
Oh, okay.
I could have done this function form here, and it would have only involved a product of two things. It would have given me the same answer. In fact, it probably would have been simpler.
Yeah.
I was just going with the most recent one. So I have 20 times e to the minus 0.7 tm minus the 7 tm. Here's another minus 7 tm, so minus 14 tm. Oh, here's another 7, minus 21. Oh, no. Let's just do the last one last. Minus 14 tm plus 20 times minus 0.7 is minus 14 tm, right? So tm times 20 times minus 0.7, minus 14. And then the last one is going to be a tm squared plus 7 times 0.7 is 4.9 tm squared. So I have that then. Now, of course, simplifying that, and so I have to find the zeros of my two functions. Well, the zero of the first one is clearly going to be tm is approaching infinity again. The quadratic will have two solutions, and I would just put, 28 plus or minus the square root of 28 squared minus 4 times 20 times 4.9, all over 2 times 4.9, and it would give me two additional times. I'm not going to do that math just because it's just algebra. You got it already?
I have a quadratic solver.
Okay, so he's going to do the quadratic solver for us, and he'd better get one time that's just a little less than 1 second, and then the other one's going to be over somewhere around 6 seconds.
20. So you got 4.8.
4.8 seconds?
Yeah.
Uh-oh.
4.87.
So 4.9.
And then and then we got 0.8.
0.8. So 4.9 or 0.8. So 4.9 should have been right around here. So I picked the wrong point. I thought it was over by 6. I'm going to blame it on the fact that I drew something else on the graph. And the other one's 0.9. That is pretty much where we had picked it. Or 0.8. So those are the ones that make sense. We have two extrema here. One of them is the maximum acceleration. One of them is the minimum acceleration. Of course, the maximum is the one that had a positive slope. So you go back, and the 0.8 was the positive slope. And the 4.9 was the negative slope. Okay, a lot of time on extrema. We're going to be done with extrema for now. And go on to finding the distance traveled. Here is the equation for that integral. So I do that integral. Notice I have plus c because I showed the integral without limits. Do we have an integral without limits here? No, we have an integral with limits. So we're going to take the part that's without c and put in time equals 10 seconds minus time equals 0 seconds. And so, come on, stop that. Stop it. So I'm going to have, and I'll put delta x here, but in a different color. Delta x is equal to, my a was 10, my b was 0.7, minus 0.7, or no, 0.7, that's right. So that's going to be in everything. Then I'm going to have e to the minus 0.7 times 10 is 7. 0.7 squared is 0.49. 0.49 times 100 is 49. 2 times 0.7 times 10 is 2 times 7, 14. Plus 2. And then minus e to the 0 times 0 plus 0 plus 2. And so I obviously can't do this in my head. Somebody want to calculate and see if my quick integral is right? No, remember, e to the 0 is 1, so I'm just going to erase it there. If you can do e to the minus 7 in your head, kudos. You're definitely better than I at this.
Remember E. Every time I need to remember, I punch it into the
2.7
calculator and-
something. It's like 2.718. I don't know.
I did it the other way, the question before. No, you said we can use the other equation instead of the one you used.
You're talking about
Yeah,
doing the derivative of
not that one, but right next to that.
doing the derivative of this. Are you going back to that?
Yeah. And got a different letter.
We can look at it later. I may be wrong. I'll admit this.
I think I'm wrong. I don't know which one. The 14's canceled out.
So I might have had a sign wrong. So it was minus 14 plus 14 is what you're saying?
Yeah. You get that?
Is it supposed to be a small number?
No.
No. Okay. I did something wrong.
Yeah.
It could be that I did it wrong. Of course, 10 over 0.7 cubed is going to be a reasonably big number, right?
It's supposed to be negative.
I didn't get a negative. What did you get, Jakes?
I got a negative, but that doesn't make sense.
Did you get a small number? Or?
No, I got negative 85.7. That was messing.
I have like 0.05. 6. Yeah.
No.
Horribly wrong.
Well, let's just, assuming I made no mistakes, of course. That there is 65. What's e to the minus 7?
It is 9.11. Yeah. Oh,
It-
this is in radians. That's why this is not a good number.
But
Well, that wouldn't matter.
that would matter.
Well, actually, on some TI calculators, it does. Actually, it's when it's in degrees that makes it different.
Oh.
But it's older.
Oh, 11 minus 8. I mean, 9 minus 11 to the e to the negative 4.
Okay, it's 9.11 times 10 to the minus 4.
Yeah, that's not.
Okay, so 9.11 times 10 to the minus 4 times 65 is still a really small number compared to 2. And so this is basically just minus 20 over 0.7 cubed. 0.7 cubed is going to be somewhere around a third, so it'd come to somewhere close to 60.
Yeah.
6.58.
Yeah.
56.8, is that what I said?
56.58.
Oh, point. So there's our actual value. And if we compare that to what we got here by doing our triangle, it's in the ballpark. They're not the same. We knew it wasn't going to be the same. Okay, so any questions about the techniques we used here? The ways we found the minimum, the maximum, the distance it traveled? Now, the function wasn't a fun function, right?
No, it wasn't.
It wasn't. So we're going to go to something that's more realistic. Now, at the end, we'll see we don't get the right answer, and I'll ask you for the improvement that would make it better. Because there's a very naive assumption I made, which anyone could say, That's not right. So what we did with the integral with the triangle, you guys remember this from calculus class? Calculus 1, when they introduced the integral or the antiderivative. And I was so lost that I just, when we had homework, it said find the antiderivative. I used the function that he introduced for finding antiderivative. And we said find the integral. I used the integrals we learned, like the rules for polynomials. Hopefully you guys learned better than me that an antiderivative is the same as an integral. Anyway, so you just find the area under. That's what an integral is doing. You're taking small dx or dt in this case and multiplying it by the function, the height, and then you add them all up. And you've added up a whole bunch of rectangles to give you the full area. Which is why when we first introduced doing the antiderivative, he said, well, you can do it with the height of the function on the left side of the box or the height of the function on the right side of the box, or you can do the average. And I didn't know what difference would it make. Well, now you do. If you do the left side and it's rising, you're going to be undershooting. If you do the right side and it's rising, you're going to be overshooting. If you do the middle, you're going to be the closest to matching. But since your DTs are infinitesimal, you know what? You end up with the right answer in all but the extreme cases. Okay, so a more practical example. So this is real life. A top fuel dragster has a peak acceleration of 5.6 Gs. What does it mean to say you have an acceleration of 1 G? Yeah, you're accelerating at 9.8 meters per second squared. If I jump out the window of the second floor, I will experience 1 G until the moment I touch the ground, under the general physics assumption that there is no air resistance. When I touch the ground, my acceleration will most clearly change from 1 G downward to a very large acceleration upward. And that acceleration is going to hurt me a lot, right? So driving the dragster, that 5.6 Gs should put some perspective to things. Has anyone been like in a centrifuge? Okay.
Like a roller coaster?
Okay, at the fair, at the fair they do like spin out thing, where they spin you fast enough that you stick to the wall and don't slide down, right? That's a centrifuge. That gets a pretty good acceleration going. I went to the Space Flight Center, Houston Space Flight Center, I think it was.
Yeah.
And they spin you up to somewhere around 4 Gs. And at 4 Gs, I was having a hard time breathing because my throat was like wanting to collapse. I was like, 5.6 Gs is a lot of acceleration. The highest acceleration I think a person has ever withstood is somewhere around 10 Gs. Flight suits, they design them to try to help you withstand these high Gs and not pass out by compressing so you don't have blood like all go down to your feet and not to your brain. Because if all the blood goes to your feet, you have no choice. You lose consciousness. So they try to do things to compare or to counter that. But that acceleration to me, first of all, is just pretty impressive. 5.6 G, it's really throwing you back in the seat. It's kind of like you're laying on your bed and your 5 best friends jumped on top of you. It's pretty much what it feels like if you're driving that dragster. So after 1,000 feet, they only go 1,000 feet because you know what? You get going really fast even at 1,000 feet. And so to keep things at least somewhat safe, they limit this distance they do the drag races so you don't have people going at extreme speeds. And then, things like the front tire fails. I know you guys I think it was Shirley Muldowney. Her front tire, she was going so fast that the rubber completely separated from the rim and then it wrapped around the axle and terrible crash. And so, they at that point, they were using bicycle tires. You know what they're not rated for? Going a few hundred miles an hour. So they've improved the tires, but they don't want them to go so fast. So they reach a maximum speed of only 330 miles per hour after 1,000 feet. If I sprint, it's not quite the same, just in case you're wondering. I don't even reach 1/10 of that, which is obvious. Well, I put it in 148 meters per second because we're in physics here. We don't use stupid feet. Just like we use acceleration in meters per second squared. And how far is 100 feet in real units? It's 305 meters. So some questions. We're going to model this using a reasonable, this is not the naive part, a reasonable model. That the acceleration drops off as you speed up. Why is it reasonable? Well, what is going to limit the acceleration of the car? Okay, speed, but what specifically, how is speed going to limit it? Wind resistance, right? Because you could always just throw gears in there and you could keep going forever if there wasn't, wind resistance. But the wind resistance, at low speeds, wind resistance is proportional to the speed you're traveling. At high speeds, it becomes proportional to speed squared. Now, I think we could all agree 330 miles per hour is probably pretty fast. But I'm going ahead and sticking with the let's see, the regular V is, I think they call it the drag equation, and the one that's proportional to V squared is the Stokes theorem. And after you get to above a certain speed, you switch over from one to the other. I'm just sticking with the simple one. But it's a pretty reasonable model. Certainly for the beginning part of the drag race, it's a very good model. Okay, so given this model, how do I find the speed as a function of time? What's the first thing you note when I say as a function of time? Change of velocity over change of time is acceleration. What I was looking for, she stepped ahead. She's one step ahead of me. The obvious thing is there is no time in this equation. I can't even tell you the acceleration is a function of time. Notice the second question is what's the acceleration as a function of time. The reason I have what's the velocity as a function of time first is because that's the logical sequence to go through. So I'm going to use what Ashley said. I'm going to use the fact that acceleration is dv dt. A0 and Vmax are constant, so what variables do I have if I replace acceleration with dv dt? I have V and I have time. Two variables? I'm pretty good. So what do I have to do when I have my equation dv dt equals A0 times 1 minus V over Vmax? That's not it. What do I have to do next if I'm going to solve for V as a function of time? Separation of variables. Now, you guys are probably, generally speaking, pretty new to this idea of separation of variables. So I will lead you through rather than asking you questions and getting you to answer. Separation of variables means I need to have all of one variable, so one variable is V, on the left side, all of the other variable, T, on the right-hand side, and I need to have my D's in the numerator position. I can't have 1 over dV and 1 over dt. I need dV and dt. So that means I'm going to have to multiply both sides by dt to get the dt on the right-hand side and in the numerator. I have this 1 minus V over V max. That has V in it. How can I move that to the left-hand side of the equation? Divide it out. Now I have to divide out the whole thing. Some people want to do stuff like, well, just divide everything by V. Well, if I divide everything by V, then this 1 becomes a 1 over V, and I left a V on the right-hand side of the equation. So I have to divide by the whole thing. So doing those two steps in one, and writing my stuff left to right like we normally do, I have this equation. Now, everything that has a V is on the left-hand side. Everything that has a T is on the right-hand side. If this is a true equation, if I integrate both sides independently, it still has to be a true equation. So now I'm going to independently integrate I put my integral on the right side of the A0. Doesn't matter, why not? It's a constant, right? So I just moved it across. So I do these integrals. The right-hand side, well, that's a cakewalk. What about the left-hand side? What's a good u substitution?
We put that denominator.
Yeah, I'm going to put the whole denominator. And if I do that, then what's du equal to?
Could you take it out of the fraction form?
Okay. No, not really. Not v squared. What's the derivative of v?
1.
Okay, it's 1, but it's with respect to v, so it's dv. Right? Because, or I say with respect to, it's not with respect to something. So you're probably not familiar with taking a derivative without being with respect to something. But that's what you're doing in a u sub, is you're just taking the derivative without being with respect to something. So it becomes minus dv over v max. Derivative of 1 was 0, so it's just that. So that means my integral is going to become the integral from u equals 1 to u equals 1 minus v final over v max. And since du is minus dv over v max, then dv is minus v max du. So there I put dv on, dv on top over my u. What's the integral of du over u? Integral of du over u is natural log. And I'm going to put my limits in right now. So it's going to be the u final over the u initial. U initial was tough, right? So that's what I have for the left-hand side. For the right-hand side, well, that part was comparatively trivial. Where's my blue pen? I guess that's the closest I have to blue. The right-hand side was just AT final. So I wanted to find my speed as a function of time. VF is my speed at my final time. So I'm just going to drop off the F's, and I'll have, I'm going to move the minus sign across. So I drop the F's. And I have that equation. How do I solve it for V? This is just algebra now, but it's not simple algebra. What's the first thing you do? Divide by V max. Let's get that out of there. Now I have a natural log. How do I get rid of the natural log? I use the inverse function of natural log, which is exponential. So now I'm going to take e raised to all this is equal to e raised to all that. And that gives me 1 minus v over v max equals e to the minus a0t over v max. Now I have to subtract 1 from both sides. Right. And then multiply by v max. And so I will have minus v is equal to now that's not the most convenient, but all I've got to do is make this a positive and that a negative, and we're good. So there we found the speed as a function of time. Whew. Wasn't straightforward, was it? But it's something we can do with calculus. If I were to give this problem to somebody in general physics, they could bang their head all week long, but they wouldn't get the answer unless they, did the call a friend. So we've got the speed as a function of time. How do I find the acceleration as a function of time? Take the derivative. Now, I am not going to take the derivative. I mean, it's not like this is the world's worst function ever for taking a derivative. It's pretty easy. Okay, I'll take the derivative. It's actually really easy. Minus and bring down the minus makes it a plus. All multiplied by V max. Well, we can cancel the V maxes. And the acceleration is A0 times e to the minus A0 t over V max. Because I took the derivative of the exponent. So the exponent is minus A0 t over V max. So the derivative of that is just minus A0 over V max. So that's what I brought down. And because there was a minus sign here, that's why it became positive.
Was that like a chain rule?
I suppose you could think of it as a chain rule using a U substitution for U is equal to minus A0 t over V max. Okay, so we've got the acceleration. Bueno. What's the position as a function of time? What would you do to find the position? This I'm definitely not going to do. You would do the integral of V. So I'd have to take this function that's boxed and do the integral with respect to time. Now, it's not super hard. It's just the integral of an exponential, right? But I'm not going to do it because it just gets a long equation. Instead, here's the answer you get when you do the integral. That's the equation for position as a function of time. Well, then we have a question. How long does it take it to cover 1,000 feet? Well, I've got the equation for distance. I have the distance, so all I need to do is solve for time. But if you solve for time, you have time here. Okay, let's change to red because red makes it stand out. Pink. There, pink makes it stand out even more, especially if you circle the time. I have time two different places, one in the exponential term and one in a linear term. That gives me what we call a transcendental equation. It's an equation that is non-analytic. You cannot solve it exactly. There's no mathematical method to solve it. Last year, even though I went through this, beginning of the semester with my students, later on in the engineering class, they had a problem like this and they couldn't figure out how to solve it. And so, they come ask the teacher, how do I solve an equation like this? You have to use another method. You have to use a numerical or graphical method. And so the standard thing to do is to break it into two functions. This function here is a function of time, and this function here is a function of time. And then you can plot them, or I put them in a spreadsheet if I want to get the answer real accurately, one against the other. That is, you have a graph that shows the left side and the right side. I put unitless because I had it in unitless. Versus time. And you can see, hey, the two functions equal each other in that time. And so then I just changed my scale so we can see more accurately. There's the time when the two functions equal each other. Hence, that's the time that is the solution. So we're able to find it, but not analytically. You can't just sit down with your pen and paper and find it. You have to use something like this. So notice I set up here the true answer is 3.7 seconds. Does that look like 3.7 seconds? No. It looks like 3.184 seconds. Okay, if my line was straight, it would. So it's not, 4.184 seconds. So it's not the same. 4.183 is the correct answer. It's 13% too long. And it also projects to give a maximum speed of 116.7 meters per second. We were given, what's the maximum speed reached by the dragster? 148 meters per second. So we can see there's a flaw with our model because our model doesn't give the right final speed. How can we make our model better so it gives A, the right final speed, and B, the right time? And it gives almost exactly the right time if you do this adjustment. Or almost exactly the right final speed and time if you do the adjustment. Well, what was naive about my model?
Wait, did you do the average?
That was naive. That's not what I'm looking for. This model actually works out well even with that. There's something else that's actually really obvious when you think about it. I gave you the maximum speed of the dragster. How is that maximum speed determined?
As
Maximum speed is DX.
Well, no, in practical sense. When you have a dragster on the track, how do you determine maximum speed? The speedometer when? At the end of the race. That's its speed at 100 or 305 meters. Is its acceleration 0 at the end of the race? No, it's still accelerating pretty well. So its maximum speed is much higher than the maximum speed that it reaches on the course. In fact, its theoretical maximum speed is about twice what it reaches in that 1,000 feet. But we don't want any cars traveling at 600 miles an hour. And so that's why they do it short. And so if you change that speed to about 305 meters per second for the maximum speed, it gives you both the right time and the right speed at the end of the race. Or pretty close. So that was just kind of naive, forgetting that that maximum speed wasn't the actual maximum speed of the dragster. It was just the maximum speed it reaches in that short distance. All right, we're out of time.